Okay, so we have this simple electric circuit, and I've kind of redrawn it to help us understand a few ideas, central ideas related to the circuit. So the first is, well, the main thing is the what happens to the electric potential as we take a little walk around the circuit. So let's say we take a little walk in the direction of the current. We don't have to walk in the direction of the current, but let's walk in the direction of the current. So we start at point A, and as we walk clockwise around the circuit, the first thing we do is we cross this battery. Now this is the way we're modeling the real battery is with an ideal battery and a little resistor which deals with the internal resistance. So we'll deal with each of these two separately. So as we start walking from this side of the battery to that side of the battery, the electric potential, so I'm plotting here on the y-axis, I'm plotting electric potential, and I'm just plotting sort of position on the circuit on the x-axis. So we go across the ideal battery, and how much does the voltage change? Well, first of all, we're going from the lower to the higher potential side. So we see that the electric potential is increasing. So we increase the electric potential as we walk from the left side to the right side in this figure. Okay, and then we walk along this battery. Oh, sorry. How much does it increase? It increases by exactly the EMF, E. Okay, so if we have a battery with an EMF E, that's exactly how much the electric potential increases. Then we walk along the wire. We neglect the resistance in the wire, so we pretend there's no resistance. So the potential does not change. Okay, this is generally true for electrical wires. If you neglect the resistance, then there's no change in the potential as you walk along the wire. Then we hit the internal resistor here, and the internal resistor, okay, so we're going to go down. Okay, we go down because when you go in the direction of the current, so the current in this figure is flowing from left to right, current will always want to go from, at least through resistors, it will go from a high potential to a low potential. So because the current in this figure is going to the right, then the electric potential decreases from the left side to the right side as we move across it. So that's why the electric potential decreases here. And then we know that the electric potential will decrease how much? Well, the current times the resistance. That will be the change in the potential. So that's this drop in the potential, the electric potential across this internal resistor. Okay, then we walk along this wire, or equivalently this section of the wire here, until we get to the real resistor with resistance R. And we know that, once again, current flows from left to right. Current flows across a resistor from high potential side, from the high potential to low potential. Okay, so because it flows from high to low across a resistor, the electric potential decreases. How much does it decrease? Well, we know there's a current I flowing through this circuit, therefore it flows through the resistor. So the decrease is exactly equal to I times R. That's what I've indicated over here on the voltage axis. Now, because this point is connected back to this point, because after all, we do have a closed loop here. Okay, everything comes back to the same point. We know that this potential must be the same as this potential, so it goes back to where it started. Okay, so V goes back to, if you want to call that 0 volts, call it 0 volts. Really, for electric potential, for voltage, it's really only the changes in the potential that tend to matter. Okay, so if you kind of look at this figure, you see that we have a rise of E, the EMF, across the ideal part of the battery. Okay, so it goes up a certain amount, but then it comes down, I times little r, and then it comes down again, I times big R, indicated over here. So because this potential is the same as this potential, because the circuit forms a closed loop, you can say that the rise, E, the EMF, is equal to the sum of the two drops, I times big R plus I times little r, or the current is the EMF divided by big R plus small r. So typically, if the internal resistance is really small, small here will mean small in comparison to the real resistor in the circuit, you can neglect the internal resistance, and so I will just be equal to E divided by big R. You can ignore little r if it's small compared to big R. This is often the case for real batteries. Okay, so let's see. So we have, again, this equation for the EMF in the circuit, I times big R plus I times little r. I can multiply both sides of this equation by current, and I know the meanings of the two terms on the right-hand side. I squared big R, this is the power, the energy per unit time, which is being put into the resistor, ultimately as thermal energy as the current goes through the resistor. And likewise, I squared times little r for the internal resistor, which is really the battery, inside the battery. So we could say this is the power, the energy per unit time, which is dissipated in the battery. Dissipated just means it gets converted into heat. So this is the rate, on the right-hand side, the rate at which heat is generated in the two parts of the circuit, the resistor, R, and the battery with the internal resistance, little r. So because of energy conservation, you can immediately interpret I times the EMF as the energy per unit time provided by the EMF source, provided by the battery, ultimately the energy provided by the chemical reaction, which is giving the battery its properties. Okay, so this equation is an expression of energy conservation. So here's a simple example. Let's say we have a battery which has an EMF of 12 volts. Internal resistance, it's a small number in ohms, so 0.05 ohms, connected to a so-called load resistance of 3 ohms. So that's just the same picture that we saw up here. Okay, so we know what the EMF is, we know what the internal resistance is, and we know what the load resistance is, capital R. Okay, so let's find the current in the circuit and the terminal voltage of the battery. Terminal voltage just means what a voltmeter would measure if you measured the potential difference between the two sides of the battery. Okay, so the current, as we just said, is the EMF divided by the total resistance. So 12 divided by the sum of the two resistances is 3.05. Calculate the current, 3.93 amps. Okay, so what is the potential difference across the actual, across the battery itself? So delta V here means the potential difference across the battery. So in this picture back here, it would mean the potential difference between point A and point B. Okay, so remember in the picture on the right, we go up E, the EMF, and then we go down I times little r, and between point A and point B, that's the potential difference across the two terminals of the battery. So you see what happens with an internal resistor when current flows through the battery. When current flows through the battery, the potential difference will be a little bit less than the EMF. You climb by the EMF value, and you come down a little bit. How much? Well, it depends on how much current you have. Depends on the current. Okay, so we've just calculated the current, 3.93 amps, and we know the internal resistance, 0.05 ohms. So E minus I times little r gives you 11.8 volts. A little bit less, you see, a little bit less than the EMF. So the EMF is 12 volts. We don't have an ideal battery. We're taking into account internal resistance. So the actual potential difference is a little bit less than the 12 volts. Okay. Next part of the question, calculate power delivered to the load resistor and the internal resistor and the power delivered by the battery. Power, okay, let's see. We know how to calculate that. So the power associated with the resistor, big R, I squared times R, plug in the numbers, standard SI units, so we get 46.3 watts. The, let's see, the power delivered to the internal resistor, meaning really the battery, as a result of the fact that the battery has internal resistance, I squared times little r, the internal resistance. Okay, so little r goes here, 0.05 ohms, so we get much less energy being created per unit time in the battery. Okay, remember this energy is created in the form of heat. Lastly, the power delivered by the battery, because of energy conservation, the rate at which the energy is dissipated in the two resistors must be equal to the rate at which the energy is being produced by the battery. And so you just sum these two numbers, 47.1 watts. Okay, so there is how you deal with a nice, simple circuit. Now, let's complicate things a little bit. Okay, we're going to talk about resistors in series and parallel. So if we have two resistors in series, it looks like this circuit that I've drawn here. It kind of looks like the same one that we had before. This time we're treating the battery as an ideal battery, so there's no internal resistance. And then we have two resistors which are connected in sequence, one after the other. Okay? Now let me say right here that these two resistors are in series. And the definition of series, the definition for two resistors in series, is that you're guaranteed to always have the same current flowing through the two resistors. And it turns out that this is achievable if there's no branch points in the circuit between the two resistors. You might not understand what I mean by that. You will a little bit later when we talk about parallel resistors in parallel. Anyway, clearly the same current's going to flow through these two resistors. Okay, so let's calculate the potential difference between point A and point C. Okay, so so VA is just the electric potential at A, V sub C is the electric potential at C. I can write this as VA minus VB plus VB minus VC. You see how this works because I'm subtracting VB and I'm adding VB, so I'm allowed to do that. Wait a minute, VA minus VB is just the potential difference across the resistor R1. So I can use our result from before. That delta V is I times R1. And VB minus VC, that's going across resistor 2. That's simply current times R2. Okay, and it's the same current, so current can be factored out. So I have I times the sum of R1 plus R2. Okay, now you can create, hypothetically, you can create what we call an equivalent circuit with an equivalent resistor. Okay, call this R sub series. And if R sub series is simply the sum of R1 and R2, then